last week we started the linear regression analysis using R. Basically, in linear regression, you have to understand how to specify the model. You also need to understand the underlying assumptions of the model and the estimation techniques. The popular one is the ordinary least square technique. And you must also be able to diagnose the model, evaluate the model performance using a number of criteria to see whether the model is of good fit or not. And beyond that, you might want to, once the model is good, it's of good fit, then you can go on now to draw inference from the model by way of looking at the T, which helps you to determine the significance of the predictor variables in the model, and the F, which helps you to look at their joint contributions. So you can draw inference, interpret the coefficients, and the most likely the final thing you want to do is to use the model to predict. So those are a number of things you have to know. Last week, we covered quite a number of them in terms of how you can run regression model, how you can check for assumptions, and how, of course, you can produce regression output, ANOVA, and others. But today, we will start from there, but also look at a number of other regression models, which we can call variants of the linear regression model. Even though we have been able to run the OLS regression, we will still start from there. So then you will also, at the end of this lecture, be able to run another type of regression called best subset selection regression. And also, you should be able to run the forward stepwise selection regression, as well as backward stepwise selection regression. These are variants of the OLS. The estimation method still remains OLS, but these models are used basically as a way of selecting the best predictors. We will talk about them very briefly. And finally, you should be able to run partial least squares regression. Why partial? OLS has a number of limitations. One of the limitations is that when you have more explanatory variables than the number of observations, then you lose degree of freedom. So, and you won't be able to get any estimate. So you have a regression that you cannot be able to estimate. So partial least square provides alternative in that case. Or when you have a perfect collinearity or high collinearity, then partial least square can also be an alternative. So in summary, we'll discuss OLS regression very briefly. Then we look at 3 subset regression types: best, forward, backward, and then we conclude the lecture with partial least squares regression. And by the way, yes, okay, when we get there, these are some of the different types of regression. I'm sure not likely most people know about this. So regression is a very wide area. So the basic, the fundamental form of regression is the linear regression. So there are others: logistic, polynomial, stepwise, ridge, lasso, elastic. There are still quite a number of others here, but some of these are also called penalized regressions. So uh, the it's a wide regression. Is a very broad area. So in the linear regression, of course, you have a model in which the dependent variable is on the left-hand side, and on the right-hand side, you have two major components. The first component is called the linear component, which you see here. And then the other component is the error component. So in the linear component, you have terms. And the first term is the intercept. The second term is the product of the slope coefficient and the independent variables. So in essence, in the linear component, you have parameters which are constant or known constants and variables which are observed. Remember also that the dependent variable is observed. But in this model, this second component, which is the error component, or which we popularly call the random error term or disturbance term, as the case may be, is unobservable. So I used to ask my students if they know the difference between random error term and residual. Most often, they get it wrong. So I will let you know the error term is unobservable, but the residual is observable. The error term is the population, the residual is the estimated value of the error term. So you are quite familiar with this. In linear regression, you may want to consider this as just a simplistic step-by-step way. The starting point for you is to look at your data, try to do a bit of graphics, do scatter plots, and look at whether there is a relationship between the dependent variable and the independent variables, and see what kind of relationship can you pick up from the scatter plot, whether linear, whether non-linear. And then do a bit of descriptive statistics, correlation, and things like that. Then number two, formulate the model in terms of what, specifying what the dependent and the independent variables are. Then estimate the model, and there is always the need for you to validate the model. Validation can be done in terms of checking the performance. And if the model is satisfactory, then the fit is okay. If it is not satisfactory, you have to go back to the original model to modify it. Modification can be in different forms. Modification could be to modify the functional form. Maybe you need to transform the variables using log. Maybe you need to add new variable to the model. Maybe you need to remove some variables from the model, and so on and so forth. So you can begin to move front and back from step 2 to 3 to 4, and then until you probably have a validated model, a satisfactory model that you can now use and present and draw inference and, of course, reach a meaningful conclusion. So another variant of regression is the forward stepwise selection, which is also one of the best subset regression techniques. So in this picture, you see how forward stepwise regression operates. So we are taking an example that you have 5 variables as your independent variables. So you have x1, x2, x3, x4, x4, x5. So in forward stepwise selection, you start the model with only the intercept. So the regression of y on intercept only is called the null model. So none of the independent variables is included in the model. Only the intercept is included in the model. Then the next step is to now add one of the independent variables to the model. And the one you will add will be the most significant variable. So the most significant variable is added. And you keep on adding significant variable until you stop the rule or you run out of variables. So at the end of the day, only significant variables are left in the model and non-significant variables are dropped in the model. So this is a forward stepwise regression. Regression will start from the null and add at a time only significant variables. Then you have the backward, which is the opposite of the forward. In the backward, initially you have all your variables here. So you will start with the full model. All the variables will be used as against the null model in the forward. So all the variables, rather, all the independent variables will be used at the beginning. So then you remove anyone, the least significant among them is dropped and put back into the basket or container. And so you are left and you run this again. Anyone, the least significant one is also left, is dropped until you are left with those that are most significant, and then you stop the iteration. So that is backward. So in the backward situation, you start with the full model and then drop least significant subsequently. The last one is the best subset selection. This time we are taking example of a situation where we have just 3 variables, x1, x2, x3 as your independent variable. So we will need to consider all possible models. One possible model will be the one that will regress y on x1 alone. So that will be model 1. One that regress the dependent on x2 alone. That will be model 2. One that will regress y on x2 alone. That is model 3. So all these ones are models with only one variable. Then another group will be those that will regress y on 2 variables at the same time. So x1 and x2 becomes model 4, model 5, x1, x2, rather x1, x3, and so on like that. So these are possible combinations of two variables from these three variables. And of course, the last one is the one that will regress the dependent variable on all the explanatory or the independent variables. So as a matter of rule, anytime you have n, or let's say k, independent variables, then you can have 2 raised to power k possible models that can be formulated from that k variables. So here k is equals to 3. So we should have 2 raised to power 3. And 2 raised to power, hello, I hope I'm being heard.
Yes, we can hear you.
Yes, sir.
Okay. Just to be sure I'm not teaching myself. Okay. So in this case, we have 3 variables, and that means we expect to have 2 raised to power 3. And 2 raised to power 3 is 2 times 2 times 2, which is 8. 2 times 2 times 2, which is 8. So as you can see here, we have 7. The one that is missing is the null model. That is the model with intercept only. So if I have 10 explanatory variables, then I will have 2 raised to power 10 explanatory variables. So most of you must have heard about 1 million regressions. So it's possible. So what happens now is that we have model 1, model 2, model 3. So we have to select the best among those with only 1 variables. Then we suppose this is model 2 that is selected. For models in the 2 variable category, we have to select the best among this. How do we do that? We can use R square, we can use adjusted, most often we use adjusted R square. Don't use R square. We use root mean square error or mean square error. We'll see how we use them. So we select the best among these models with 2 variables. Let's say we select model 5. Then, of course, no one is competing with this, so it's going to be selected. So at the end of the day, we have to also evaluate the performance of model 2, model 5, model 7, and that will finally lead us to the selection of one of them. So this is what we call the best subset. At the end of the day, we will consider these 2 variables, variable 1 and variable 3, as the best subset of these 3 variables. So for partial least squares, the optimum number in the partial least square is a technique that allows us to predict the dependent variable when you have very large set of independent variables. This kind of situation do occur in some research in biology, maybe I've forgotten the name, in biology, or even some other, even in Greek and so on. You know, so you can, when you can have a situation where you have more variables as your independent variable than the number of observations that you have. So when that happens, you can use the partial least square regression. This technique identifies linear combination of predictors that meet 2 conditions. The first condition is that they explain the linear combinations. They can properly explain the initial predictors. And 2, they are related to the response of the dependent variable as well. So the technique generates linear combinations that are related or capable of explaining the predictors, and at the same time, they are related to the dependent variable. So the optimal number of components that generates the best model on the basis of mean square error. So we use the lowest mean square error as the basis for choosing the optimal component. And that is done using the technique of cross-validation. I know this may be strange to some of you, but those who are also used into machine learning will understand the concept of cross-validation. We don't intend to go deep into that, but this is just to at least uh, uh, expose some of these things to you. You can possibly learn more, but you will know how to implement this tonight. So the partial least square regression is most useful in some fields of research where the number of predictors is greater than the sample size. Yes, for instance, in cancer research in particular. So this is the rundown of the slide. We can now go to the, but before we go to the R script, R studio environment, I would like to hear your questions. Is it clear? Do I move on?
Yes, sir.
Thank you very much. So right now, if you have been able to, download the data and the script file, then you can click open as usual. Click open and navigate your way to your working folder. Look for the R script module 5A linear regression. Click it and click open, and then you will be able to have the script file. And make sure also in your working folder that you have this file, community crime, compcrime.csv, so that you'll be able to flow. So I've done that. At this stage, you should know how to set your working directory. So, but I will still teach you. So to set your working directory, you go to session and you go to set working directory, choose directory, and then locate where your working folder is, which in my own case is the desktop. That may not be where your own is, but you should be able to locate where your own is. So this is my working folder, PiLAF 2022, and then I click open. Once I click open, I will be able to get the address here. So in your own case, you need to copy this. You need to copy this, whatever appears in your own, copy it and paste it over whatever you have in line 2, so that it will tally with your own, address. So let's open that data, which is comcrime.csv, and I'm going to use the read.csv function, and I will save it as R data frame. Is somebody raising up hand again? Adesanlu, you are still raising up hand. Just speak. I give you permission to speak if you have something to say. So, so the data will be read and saved as R data frame with the name CRIM. And let's read it. So if it's successful, it appears it's very slow, but let's wait, still working. Maybe it's looking for it. So it's been successfully read. So in that data, you have 2,212 observations or cases, and there are 17 variables. If you click this blue arrow, you can see the variables. So these are the variables. It should be more than this, I think. So, but you can also view it if you click this. If you click this, it will appear here, and you'll be able to see all the variables that are loading. The system is just too slow today. So these are the variables. There are 17 of them. These are the variables. So it's about community crime. And some of the variables there represent the burglary per population. So in the first community, you have 114.85 burglary per 1,000 population. So this is the population density. This is the number of streets. This is the number in shelters. This is house that are vacant, number of vacant houses, and so on like that. And this is the household size, maybe average household size. This is the race percentage of Black race. This is percentage of white race in that community. This is percentage of Asians, Hispanics, and so on and so forth. So this is about the data. Let's go back to our model. In line 7, we try to use only complete cases. There are probably missing ones, but I doubt. So if you look at, so you have 2,212 communities. So the line 7 command is only going to use complete cases. So if we run that, it will create a new variable called crime2, which has complete cases. Interestingly, no cases, all the cases seem to be complete. So we can also check the internal structure of the data. So this is it, giving us the list of the variables and the type of variable, whether number, integer, and so on, mostly numbers and integers. So our dependent variable that the variable we want to really explain is the burglary per population. We want to know, or we want to use our model to determine factors that determine or influence burglary in the community. So what are those disposing factors that drive or that are responsible for burglary, community burglary, so to say. So we are using burglary per population as the dependent variable. So this is the variable we are using as dependent variable. From last class, you know that variable must be one that is measured on a continuous scale. So that's why you can use the linear regression. And we are going to use the remaining variables so that out of 17 variables, one is going to be the dependent, the remaining 16 will be our independent variable. So to do that, we will use the LM function, and that function is available in the start package. If you go to your packages, you look at the packages, there is a package called starts. If you click it, you'll see the documentation for that package. And in the documentation, that's where you have the LM function. The LM function. So so this is the function LM, and it is used to fit linear models. If you click it, it will give you the documentation for, yes, so this is LM in the start package. And LM is used to fit linear models. So it can be used to carry out regression and so on like that. And this is the usage. The first thing is the formula. So whatever you see here, they are called the arguments. So each argument is explained here. So the formula argument is what is explained here. The data argument is what is explained here. So you need this at least, even if you don't specify the rest, you need to specify the formula and the data. So how do we do that? So this is the LM function, and then we specify the dependent variable followed by the tilde sign. And you see, I use dot here. I use dot, or rather you use dot when you want all the remaining variables in the data frame to be used as the independent variable. So otherwise, you will now need to start taking each of them and put x1 plus x2, x2 plus x3, and so on like that. But the dot tells R that I want all the variables except burglary population to be used as the predictor. And then you specify the data. The data we are using is the data frame that we have here, crime 2, which is the data frame that contains the complete cases. So now we can run this. The result will be saved in the fit object. So I run this, and the result is here. To get the result out, I use the summary function. So I say summary, and then I have the fit. I'm actually calling out for the content of this fit object. So I run, and that gives the result. So in this result, you'll be able to see the command you use, the syntax you use, and then this gives you this analysis of the residual. So the minimum residual is this, the maximum residual is this, the first quartile residual, and the third quartile residual. This is the median residual. In a way, this tells you about the distribution of the residual. I'm sure you discussed about that in the last class, in the previous class. So this is and from this result, we can see those with 3 stars, they are 100%, we are 100% confident that they drive crime or burglary in the community. So household size is very significant. Race percentage of Black race also is a driver of burglary. but percentage of white and Asian, so doesn't, they don't drive burglary. That's what the data is saying anyway. So don't feel bad. So we can see those that are very significant, and those that are not so significant. And these are the diagnostics, the statistics, or the criteria or the values you need to diagnose the model. This is the residual standard error, and you have 2,195 degrees of freedom. That is the number of observations minus the number of parameters that you are estimating. Then you have the R square, which says about 48% of the variation in burglary is accounted for by these 16 variables. This is the adjusted R square. The F statistics is 127.8 and it's very, very significant, which means that jointly all the variables explain burglary in the community. So this is all. If we are interested in the ANOVA, we can run line 17. Line 17 gives the ANOVA, which is the analysis of variance table. So here you can, just as we have done, you can see which of the independent variable contribute to the explaining the burglary or community burglary, is the case may be. So that is that about linear model. There are other things you can do from here, checking assumptions, but you have done that last week and all of that. So that's not our focus at this moment. The second model we want to consider, I hope, if there is any question, please let me know. Let me know. If there is any question, let me know. Let me see the chat menu. You can also put your question in the chat menu. I can see Muinat is saying SEM, CEPHA, and NEPHA also regressions. What do you mean by okay? Similarly,
those are structural equation model.
Structural equation model, yes. Structural equation models, yes, they are also regression models. Any model that you have two sides, you have the left-hand side, you have the right-hand side is a model. And you are explaining the left-hand side variable. And you are using the right-hand side variables to explain the left-hand side variable. So any model of that nature is a regression model. But you could have a single equation model, and you could have a system of equation model. So in a single equation model, you have just one dependent variable, and you could have multiple independent variables. But in a system, you could have more than one dependent variable. And so you have system of equations. So SEM is a structural equation model, and it's also a form of regression. The same thing for the confirmatory factor analysis and so on.
Yes, thank you, sir.
Yes, thank you. And I can see Rawa Victor also raising up. And can you unmute and speak?
Good evening, sir. Thank you for the opportunity to ask questions. I want to ask, okay, for example, now we have 2,212 observation. Let's say we want to choose gravity per population as our variable, but we don't want to use all of the
as our
other variables as our independence variable.
yes.
How, like, let's say we don't want to use everything, just like we did in this example. We don't want to use all of the other variables as our independence variable.
Yeah.
You get me, sir? So how are we going to go about
Yes,
that?
yes, I can get you. So thank you. That's a very good question. And actually, that's one of the questions we want to answer before we finish this class. One, when you are modeling, the first thing you do is to think of all possible factors that can determine your dependent variable. So when you are doing research, your dependent variable is actually your focus variable, is the variable of interest, is the variable you want to explain. And you are looking for factors that will help you to explain the variation, why that dependent variable is varying, why it's behaving the way it is behaving. So you might come up with several variables that you consider. Some of them can be suggested by literature, some of them can be suggested by theory, some of them can be suggested by intuition, some of them can be suggested by your own experience, and many other factors. So you are likely going to start with a very large number of variables. So one of the things you want to do is, if you use the approach we want to use now, you can start eliminating them. For instance, number of urban is not significant in this model. So you can eliminate this from your model. Is that clear? You can also eliminate this from your model. So those that are not significant, they don't have to be in your model, because we talk of parsimony. Parsimony means making your model to contain only the smallest number of predictors that will have the best predictive power. So if you put 20 there and the predictive power is the same thing as when you put 7, so you are only having a bogus model. So you only need to put variables that ensure high predictive performance of your model. So to answer your questions, yes, once you run, you start with very large number of predictors, then you can remove them if they are not significant. In econometrics or other fields, you must also combine significant with theory. Sometimes also, if the theory says the variable must be there and it's not significant, you still retain that variable. But so practical significance is more important than statistical significance. Is that okay? Somebody seems to be anxious to say something too.
Thank you, sir.
Okay, that's good. So let's move on. We still have a lot to cover. The next type of regression is the best subset. And this will further answer your question, because in this best subset regression, we are actually looking for the best among these 16 predictors that we should retain in our model. So that's what the best subset will help us to choose. And to do that, we need the LIPS package. So you can go to packages, just be sure that that package is there, LIPS. If it is not there, go to install and type LIPS. So, and suggestions will come, choose one and then install. But I think I have it. So I just need to load it. To load it, I need to run 26. So I run. So it's been loaded. Then in that package, there is a function called regression subset function. And that will be used just like the way you use the LM function. You have to state the dependent variable, follow, this is the formula side, where you state the dependent variable, tilde, and dot to represent all of them. So the data is CRIM2, and then there is an argument here which indicates the maximum number of variables. Of course, the maximum number of variables, since we have all of them to be 17 and we have used one as dependent variable, so the maximum number is 16. So NV max means maximum number of predictor variables. So we can run this now, and then the result is already saved in fit, and we can use the summarize fit function to get the result out. So we run this, and then we get the result. So this result, you have to understand how it's going to be interpreted. So if you go back to my explanation here, you will understand in the best subset, since we have, in this case, 16 variables, which means we have x1, x2, x3, up to x16. So there will be 16 groups of models. The first group will be those that will contain only 1, 1, 1, 1 predictors. So then the second will be those that will contain only 2, 2, 2, 2 predictors. Then the next will be those that will contain only 3, 3, 3 predictors, and so on and so forth. Up to those that there will be the last one, which will, of course, will be only one, which will contain 16 predictors. So it's going to start from those that has 1, 1 predictor and choose the best among them. So if you go back to this result, you will see in the class of those that has only 1 predictor, the best one will be given, the one that is the best is, you will see star there, which means only race per white is significant in these regressions with only 1. So for those with 2, you can see percentage of black race is significant. There should be 2 of them. So for 2 again, you can see percentage of this variable. I can't remember what the name is. Then for those that are 3, there should be 3 of them. Household size is significant. Race percentage of white is significant. And of course, for 3, yes, the percentage of population under the province or wherever is significant. So there will be 3. Again, for 4, there will be 4 of them, and so on, until you come to the last. Now, even if you have problem understanding these results, you can use the function summary of the adjusted R square. So it's going to give you a summary of the adjusted R square for all the models. So if I run this, it gives you this, the adjusted R square for the first model selected among the ones, for the second one, third, fourth, fifth, sixth, this is the 7th, this is the 13th, this is the 14th, this is the 15th, and this is the 16th model. So it has, what you see here, using R square, it has is giving us among the models containing only 1 variable, the best in terms of R square is having 31.9 or 32% predictive coefficient of determination. Well, actually, this is adjusted R square. So this one also, you will see that this adjusted R square initially is increasing, and if you look at it, up to a point, it started decreasing. So, and the best one will be the one with the highest. So we can use it, the code in line 36 to choose for us the one with the maximum adjusted R square. So this one will give me number 12. And which one is number 12? It's actually referring to this. And if you notice, this one keeps increasing. This is 7 increasing. This is 11 increasing. After this point, it started decreasing. So this is the maximum, therefore. So this, the model that gives with 12 predictors, the model containing 12 predictors, as far as this model, as this analysis is concerned, is the one that gives the best model in terms of the adjusted R square. So we can use the command in line 38 to now obtain the coefficient of that model with 12 predictors. So we can run that. So this is the coefficients. So we can see household size is there, percentage of black race is there. So it has eliminated, out of 16, it has on its own removed 4. So we are able to prune down the number of predictors from 16 to 12. We can still go down because, let's say, of course, you see this is the adjusted R square for this. As if I use 8 and I know that it doesn't really, by using 8, I'm still able to achieve the same level of goodness of fit, then I can still use only 8 instead of 12, just to make my model as concise as possible, as parsimonious as possible. So in this case, let's try 8. So if I'm using the best 8, then these are the ones: household size, race, percentage of black race, and so on. So these are the most significant variables that are driving burglary, community burglary. So this is how to carry out the best subset regression. If you want to see the significance and so on, then we can now use the LM function. So if I use the LM function, though it's not written here, all I just need to do now is to say fit 8. I can say fit 8. And the assignment, and then I use the LM, and I use the variable, which is what the variable burglary, that's our dependent variable. This is our dependent variable. So I can have bug population. Then I have the tilde. This time I can't use dot again. I can't use dot again because I now have to choose these variables: household size plus race race percent black plus race percent Hispanic plus urban plus percent. So I have to list all the 8, then plus, and finally plus. So these are the 8. And of course, I have to put the data, which is cream 2. So I can run this error. Okay, the bug. Okay, this should have been capital P, L capital P. So that is fit 8. I can then use summary fit 8 to get the result. So this, you will see that in this result, all of them are significant. You can see that all of them are now significant. So I've been able to pull down the variables and have only those variables that are significant in terms of driving burglary. So the most important drivers of community burglary are these variables. And this one is able to give me adjusted R-square of 0.4784, which is saying that about 47% of variation in burglary is explained by these 8. So that's how to do that. Let's now move to the forward regression. The only thing we need to do is we still use the regress subset function, but this time we will just add the argument method. This argument, we will choose forward. If we don't include that argument, just like we did here, we didn't include that argument here. So once that argument is not included, the model will simply do the best subset. So let's run line 53 for the forward stepwise selection. I run and I get the summary and I get the output. It's just like before. The interpretation follows like before, and you can now summarize based on adjusted R-square, and we can determine which of the adjusted R-square is the maximum. And it says it's 13, that is this one. You can see it's 47.89. It's about the same thing as the last one we did. So that's how we obtain that. We can choose a lower one if we so wish. We can. This is 7. This is 8. This is 9. You will notice that this is 0.47, but even 0.47 starts from here. So you could still want to say, okay, 47 is still okay, or 0.47 is still okay. So you could just choose 8, which will just be the one we obtained, just similar to the one we obtained before. And so we have this result. The backward is the same thing, only that in this function, in the regress red subset function, you are only going to indicate the argument method to be backward rather than forward. So you can run this and then you get your results and the output. Of course, you can, on the basis of adjusted R square also, you can obtain which model has the maximum adjusted R square. It's actually 12. And you can get the coefficient of that. This is the coefficient. So that's how to run the backward stepwise regression. So that's the fourth type of regression so far, the ordinary least square regression, which will give you almost all the you have the output, and you can just use significant, decide which variable to include or to exclude based on their level of significance. Or you run stepwise and or best subset or forward stepwise to be able to select the best subset of the independent variable. The last is the partial least squares regression. So we need the package PLS. So require package, check if you have that package PLS. So you can go to LMN or P. So I have it. If you don't have it, then go to install and type PLS. And you see the suggestion PLS. You can click it and you can install. But if you have it, you don't need to install. So here it is, partial least squares and principal component regression. So you can learn more about this in case you find it attractive. It's a very useful package or technique. So in it also there is the technique called the cross-validation technique. There are different methods of doing cross-validation. In machine learning is popular, but the purpose of this is not to introduce it to machine learning. But there are two folds. You can have two folds in which you split your data into two. You call the first one the training set, and then you call the second one the test set. You can split into three. You can have the training set, the test set, and of course, the validation set. So you can continue like that. So the general one is called the K fold. So you could have K to be 5 to be 6. So K can be 10. So in PLS, it uses K fold. So K generally is taken to be 10. There are a lot of things you might need to know about that. So the cross-validation helps to determine the optimal number of components to choose. So we will now run line 58 using the function PLSR, that is PLS, partial least square regression. The package itself is PLS, but the function you are using is the PLSR. So if you want to know more about the PLSR, just click the PLS package and look for PLSR. This is the package, partial, least squares, and principal component. So if you click this, you'll see the documentation, how to use that function. So to use it, you need to state the formula and indicate the method. That's precisely what is done here. So this is the formula which will specify the dependent variable, followed by tilde, and then dot here means include all the remaining 16 variables. And the data we are using is pin 2. The scale is said to be true, which means it's going to standardize the variables. That's what scale means, refers to there. And then the validation is CV, which is very important for you to indicate. And then you run this. So still running, I take a while. It's done. And then so we can, the result is saved in feet. So line 90 will help us to get the result. So this is the result. This is the result. So you have the X dimension, the Y dimension. The X dimension has 2,212 rows and 16 columns. The Y dimension has 2,212 rows and 1 column. So this number of components determined is 16. And these are the, so the cross validation uses 10 random segments, which simply means that the K fold, K there refers to 10. So 10 is the value of K. So this is the first component, this is the second component, is the third component, and this is the last, which is the 16th component. Each component, including intercept, has its, this is the cross validation, which is actually using the root mean square prediction. So this is the adjusted CV. This is the CV. This is the adjusted CV for all the components. So there will be, you have the result also for the training, which gives the percentage variance explained. So and the first component is able to explain 31%. The second able to explain 48%. The third able to explain, so for the X, and this is what they are able to explain for the dependent variable. Remember, we said that there are two conditions. The first condition is the component must be able to explain, to look at my explanation. There are two conditions. They must properly explain the predictors. So the first part here is giving the percentage of the predictors that the component is able to explain. And the second condition is that they are related to the response variable as well. So in essence, you see the percentage of the dependent variable or the response variable that the component can explain. So that's the summary of that. But we can easily see the picture more clearly in a plot. So I'm going to create a plot which will help us to now determine what component we should choose. We can choose component based on the R square, based on the mean square percentage, mean square prediction, or the root mean square prediction. So I'm going to, in line 95, is going to create or partition the plot area into 1 row, 3 columns. So let's do that. A partition area, you won't see it, but let's do this first one. Run this, and then let's plot it. So it's going to plot the CV for train and the CV and the train. That is the CV you see here. The CV. So you see it's going to plot the CV, and then also for train I showed earlier. So you have the CV, and you also have the train. So it's going to plot the two. Again, let's run 100. This time is for, this one is actually for the R square. It's for the R square. So we run 100. 100 is for mean square error prediction. And then we can plot it. This is it. The next one is the root mean square error percent. We run it and we can plot it. Now we can zoom just to have a good look and to choose the best among the components. So what we normally would prefer is the CV. So we can see that as the number of course, there are 16 components. So on the x-axis, that's where you have the components. And here is where you have the R square. So the R square, as the component initially increases, the R square also increases until it starts stabilizing. Then here you see the R square terminates here. So the value is somewhere something greater than 5, but less than 10. If you look at the mean square error prediction, this is here, and this axis, you have the number of components. Now, using the CV, we see initial drop because we expect the best model is the one with the lowest mean square error. Just as in R square, the best is the one with the highest R square, or the highest adjusted R square, the case may be. So we can see the CV drop and tends to rise just very small. So again, we can suspect the minimum to be between, in this range, something above 5, but also less than 10. The same thing if we use the root mean square error percent. So again, we see that the least is probably above 12, above 5, and below 10 to look at the CV there. So therefore, we can try 8. So, and then we run line 8 to get the coefficient of 8. So I can run line 8 and then get the coefficient. So these are the coefficients. You can compare these results with what we have previously. In terms of, not in terms of the values, but rather in terms of the variables that have been selected. You will see that they are almost identical. So this is how to run the partial least square regression. So once we have finally selected the number of components we want to choose, and we now want to see the details, then we run line 112, which we now use the partial least square regression function. Then you specify the formula as usual. You specify the data. You specify the scale, which means it should be normalized or standardized. And then the number of components you now want to choose, which is 8, so that you can have the full result. And that is going to be, so the result is saved in fit 2, and then in 113, you have the result. So you see the 8 components that have been selected, and 114 gives you the coefficients. So you can be able to interpret the coefficients. So this is for the model with 8 components. Thank you very much. This is the end. In summary, what we have done is to look at variants of regression models and how to use them, beginning with the ordinary least square. We have also used the best subset regression, the forward, the backward, stepwise regression, and now we have used the partial least square regression. Thank you.